So in this video, we'll be looking at a very basic concept in physics known as the velocity time graph, also called the VT graph. But before then, let's look at a basic definition. What exactly is a velocity time graph? By definition, a velocity time graph is a graph that shows the velocity of a moving body at different time intervals. So when we talk about the concept of a velocity time graph, we're talking about a graph that shows the different velocity of a body at different time intervals. Okay, so that's what a velocity time graph is. Let's look at what it actually looks like because it's a graph. So let's look at a basic diagram that shows what a VT graph looks like. Okay, so this is a basic diagram of a VT graph. Okay, so for a velocity time graph, you can see this part here, which shows the acceleration of the. You can see this part here, which shows the acceleration of the body. Okay, you can also see this part here, which shows the uniform velocity. You can also see this part here, which shows the deceleration of a body. So for a VT graph, we either get acceleration from this kind of slope, or we get uniform velocity, that's for this kind of slope, and of course we can also get deceleration for this kind of slope. Okay, all right, so having said that, let's look at two very important concepts in the VT graph. Okay, let's note two very important points for a VT graph. All right, so two very important points about a VT graph. The first point is this. The first point is the concept that the velocity of a body is being plotted on the vertical axis. All right, so we plot the velocity of a body. So velocity, probably in meter per second, is plotted on the vertical axis of your graph sheet, while the time, right, the different time intervals in seconds, they are plotted on the horizontal part, or the horizontal axis of your graph sheet. Okay, so don't forget, velocity is plotted on the vertical part of the graph sheet, while the time intervals are plotted on the horizontal part of the graph sheet. Now, having said that, let's look at the second thing to note about the VT graph. Now, the second thing to note about a VT graph is that the slope of a VT graph usually gives two types of acceleration. The first one is called the normal acceleration, as we know, right? So the slope of a VT graph could either represent either an acceleration or a deceleration. So these are like two possible slopes we can get from a VT graph, an acceleration or a deceleration. So how do we know the difference? Well, it's quite simple. If you have something like this, where you have the slope going like this way, where you have, of course, we said velocity is plotted on this part, the vertical parts, while time is plotted on the horizontal axis. For a slope like this, where velocity is increasing with respect to time, the slope of this would be an acceleration. All right, so you get acceleration by taking the positive slope of a VT graph. For deceleration, it's the opposite. So we have your VT graph such as this, velocity and then time. We said velocity is on the vertical axis and then time on the horizontal axis. In a case where you have the value of the velocity decreasing with respect to time for a slope of this nature, like this, all right, what you have here is called a deceleration. So the slope of this graph gives a deceleration. So that's like the basic difference. Okay, so know when you can find acceleration and know where you can find deceleration in a VT graph. Okay, if the velocity is increasing with respect to time, an acceleration will be recorded. Why, if the velocity is reducing with respect to time, as in this case here, a deceleration will be recorded. So if you go back to the original diagram that I showed you earlier, which is this diagram here, so you can see your acceleration at this point here, where velocity is increasing with respect to time like this. That's an acceleration. Okay, if there is no change in velocity, that means the velocity moves in a constant pace or the constant value like this. It is called a uniform or a constant velocity. At this point, there is no acceleration, there is no deceleration, just uniform or constant velocity. Meanwhile, if the velocity is reducing with respect to time, giving you this kind of slope here, what you have here is called a deceleration. Okay, so know when each of them comes to play. All right, so having said this, let's take some few examples on the VT graph and try to solve problems on the VT graph. All right, so let's take our first example. So you're given a VT graph such as this, a velocity time graph such as this, okay? And you're asked from the above, calculate number one, the acceleration, number two, the deceleration, number three, the total distance covered. So how do you solve this? Let's start with the first one. Then number one, let's get acceleration. Let's start with acceleration. Now, acceleration A, as we know it, is equal to change in velocity all over change in time. All right, it's a basic formula. And change in velocity is simply the final velocity minus the initial velocity all over the final time minus the initial time. Now, to get these values, our first step would look at the point where this occurs. Okay, so we look at the point where the acceleration occurs in the VT graph. If I come to this VT graph here, we can see that acceleration occurs at this point here, this region here. That's the OA region. So this OA region here is what shows acceleration, this region here. So that means what you do is this becomes your V1. So this is V1. That's where the velocity starts. This is V2. A here is V2. That's the part where the acceleration ends. Also, when it comes to time here, this also becomes T1. That's where we start counting time. Also at V2, which is this point here, if I trace this down, we have this point here. So this becomes your T2. So here is your T2, okay? Because this is where the acceleration ends. If I trace this downward, I will have this point. That becomes T2. If I pick in values there, V2, I'll trace V2 to my left-hand side. That's here. And the value is about 10. So V2 has a value of 10. V2 is 10, so I have this as 10. So I have V2 as 10 minus, let's get V1. If I come to this, you can see that it starts from the origin, that's here. And at this point here, V1 is 0. That becomes 0. So V1 is 0 all over. Let's get T2. T2 is the value of the time at this point here. That's where acceleration ends, this point here. If we trace this down, you can see that the value of T2 is 4. So that becomes 4. So I have 4 minus T1 is the value of this point here, which is also this. Okay, T1 is this point here, this one here. So you can see the value there is 0. So T1 is minus 0. If I punch this, 10 minus 0 gives you 10 all over. 4 minus 0 gives you 4. And if you punch 10 over 4, that gives about 2.5. So I have the value here as 2.5. Now go back to the units. Observe that velocity here is in meter per second, while time here is in seconds. Okay, so if I do meter per second all over second, what you get is meter per second squared. All right, so with this, we've gotten the value of the acceleration. Let's get the second one there. The second one says we should get the deceleration. So II. Let's get deceleration. So deceleration. Also, deceleration and acceleration are the same thing. The only difference is that deceleration is the kind of acceleration that brings a body to rest, which means it's literally a negative kind of acceleration. But then it has the same formula as acceleration, which is change in velocity all over change in time. Now, if this is true, this will be equal to change in V becomes V2 minus V1 all over T2 minus T1. For deceleration, we expect that the value should be negative, okay? Because deceleration is called negative acceleration. It is the kind of acceleration that brings the motion of a body to rest. Let's pick out this value from our graph sheet. Now, the first thing we have to do is to identify where exactly do we have deceleration in this diagram. From our diagram here, you can see that deceleration occurs between C and E. All right. So this is the point where deceleration occurs. That's C and E. All right. So that means deceleration occurs in C and E. So deceleration actually starts from this point. It starts from this point here. So this become your initial, right? V1 and T1, and then ends at this point here. So this becomes your final V2 and T2. Let's pick out value. That means here's actually V1 in this case, and this is V2. This is V2. All right, V1, if I trace this here to the vertical axis, trace this, this is the value here, which is 10, right? So trace this to V1, you have 10 as your answer. So V1 is 10. What about V2? V2 is this point here where the body comes to rest. And this point where the body comes to rest, if I trace this to this point here, I'll see that the answer is 0. That means V2 is 0, while V1 is 10. So V2 minus V1 becomes 0 minus 10. So I have 0 minus 10 all over. Let's get T2 and T1. For this same diagram, we said this is your initial. V1 and T1 will be here. V2 and T2 will be here. Let's get the final values. For T2, T2 is the value of time at this point here, which we can see it's 20, while T1 is the value of T at this point here, this C where it starts. If I trace this downward to this point here, you can see that from here, trace this down to the time here, you can see the value there is 8. Okay, so let me move this way here. So you have the value as 8. In essence, we are saying that V2 is 20, while V1 is 8. So the denominator becomes V2, which is 20 minus V1, which is 8. Let's put value there. 0 minus 10 is minus 10 all over. 20 minus 8 is 12. So I have minus 10 all over 12. Let's punch this value. This will be equal to minus 10 over 12 gives you minus 0.83. Because this should be in meter per second squared too. Right? Also a type of acceleration. Okay. 0.8 meter per second square, but we don't put the negative. All right, so we just write this as 0.83 meter per second squared. The negative means deceleration, and that's why I said deceleration is simply negative acceleration. So when you get the negative here, simply ignore the negative, just use the positive value. So it means that in this question there, the deceleration is about 0.83 meter per second squared. Let's look at the final question there. Final question here says, find the total distance covered. All right, let's get total distance covered. To get that, let me take off this part first. Let's get total distance covered. Let me take off this part first. Taking this off. All right, so I. Let's get the total distance covered. Total distance covered. Now to do this, to get the total distance covered, you have to look at, you have to segment this into different segments. The segments will simply be the different shapes. This becomes segment 1, this becomes segment 2, and this becomes segment 3. All right, or you can call it part 1, part 2, and part 3 of this diagram. Usually you have different basic shapes. All right, let's look at segment 1 for, or let's call it section for section 1. Section 1, as we can see here, is a triangle. The triangle here is OAB, right? So O here, A up, B down. So for section 1, which is triangle, that's triangle OAB. To get the distance, we have to find the area of the shape. And this is a triangle. So the area of the triangle becomes half times the base times the height. All right. So for this OAB, what's the base? The base for OAB, which is section 1 here, starts from this point here. It starts from this point, which is 0, and then it ends at this point, which is 4. So if I have the zeros, if I have the number from here to here, which is 0 to 4, we can see that the base is from 0 and it ends at 4. That means the breadth or the base is about 4 in value. So I have half times the base, which is 4 in value, times the height. The height is simply the distance from this line here, right, from the horizontal line to your apex point or the highest point A. From the horizontal line 0, which is this part here, 0 up to the highest point, which is this part here, 10. That means if I move from 0 to 10, the distance covered is 10. That means the height is actually 10. So I have this as your value. If I multiply this, this will be equal to half times 4 times 10 gives you 20. And this becomes meters because you're looking for distance. Now, this is the distance for section 1. Let's get for section 2. For section 2, let's look at section 2. What shape is section 2? Section 2 here is a rectangle. You can see this as a rectangle. The rectangle here is ABDC. All right, so this is a rectangle ABDCA. All right, so you have ABDCA. All right, for section 2, we have a rectangle there. The rectangle there is ABDCA as a rectangle. All right, that means the area of this part becomes the area of a rectangle, which is length times breadth. Let's get the length of this part and also the breadth of this part. From this diagram here, the length is simply from here, right, from this top here to the bottom of this, which is from 10 to 0. So the length of this part like this, from here to here, if you trace this, it should give you about 10. Okay, just trace this. This is 10 here. So you're moving from 0. Remember that this 4 is for time, right? So trace this to the vertical axis. So trace this from here to here. This is, if I trace this way, I have 0 here. Trace this way here, I have 10. So the length there is about 10. That becomes 10. So I have this as 10 times. Let's get the breadth. The breadth of this triangle for section 2, if you look at this, the breadth starts from number 4 and ends at number 8. That means the breadth is simply this distance here, all right, which is from 4 to 8. So if I have a number from 4 to 8, what is that distance? Distance from 4 to 8 is simply 8 minus 4, and that's equal to 4. So the value there is 4. That's your distance there. All right, so we've gotten that value there as 4. Let's take it back there. So my breadth in this case is 4. That becomes 10 times 4. That becomes 40 in meters. One final part, which is section C or section 3. Okay, let's take this down. For section 3, for section 3, what shape is section 3? If I go to section 3, the shape here, we can see is a triangle here. Okay, let me take this part off. This is off. Take this part off a bit. Okay, section 3 there, the shape is a triangle, and the triangle here is triangle CDE. All right, triangle CDE here. All right, so let's take triangle CDE. So triangle this way, CDE. Now, since this figure is a triangle, the distance becomes the area of a triangle. Area of a triangle is half times base times height. That's equal to half. Let's get the base of section 3. The base of section 3, you can see that this base, it starts from 8 and ends at 20. All right, so that means the distance from this point up to this point here would simply be 20 minus 8, and that's equal to 12 as your value. All right, so the value there is 12. All right, so the base there is 12. I will come here. Half times the base is 12 times, let's get the height. The height of section 3, again, section 3 for this, when we talk about the height, we talk about the vertical distance, starts from here and ends here, right? Trace this to the vertical part. This part, when we trace this, was equal to 10. This part, trace it to your left, that gives you 0. So that becomes 10 minus 0. And if you point 10 minus 0, your answer gives you 10. So the height is simply equal to 10. So I have this as times 10 here. If I multiply this, I have half times 12 times 10. That would give you 60, and the value is in meters. So hence the total distance would be equal to, you add section 1, the value of section 1, which is 20 meters, becomes 20 plus the value of section 2, which if you add it for section 2, the value was 40. So this plus 40 plus the value of section 3, which we got here as 60 meters, so plus 60. All right, so let's calculate this. 20 plus 40, that gives you 60, plus 60, that gives you 120 meters. So the total distance covered by this particular body or this particular diagram here is 120 meters. So this is how we solve this question. All right, so this is the basics for VT graph. Let's look at something much more complex. Okay, so let's see this diagram here. This one is a bit more complex than the first one here. So here's a diagram, a VT graph. You're asked to, from the above, you're asked to calculate number 1, the total distance covered, number 2, the average speed, number 3, the retardation, number 4, the maximum speed attained during the motion. Okay. All right. To get the solution of this one here, simply join the jam/WAEC class. Okay. I'll leave a link to joining the jam/WAEC membership in the video description, or you can get it from my website www.jonaemmanuel.com/courses. You see the jam/WAEC course. Okay, you can also get it there. That's where you see the complete solution to this question. All right, I'll leave the links to both my website and the link to join the jam/WAEC class in the video description. All right, so check video description for the links. Okay. I'll also add other videos. Okay, so you get other complex videos on VT graph. You also get word problems on VT graph, such as this one here. All right, such as this one here, where you see word problem on VT graph, and I'll teach you a step-by-step process on how to draw the diagram if you're not given the diagram. All right, to get the complete tutorial video on this particular question and the other video, simply join the membership. As I said, I'll leave a link in the video description, or you can also get it from my website www.jonaemmanuel.com/courses, and then you can check the jam/WAEC classes. Okay. All right, so if you enjoyed this video, please make sure you leave a like. Okay, so hit the like button. All right, like this video, leave a comment, tell us if you enjoyed this video, and also suggest other topics you'd want to see. Don't forget to, if it's your first time, please do what to subscribe. All right, subscribe and hit the bell icon so that you get notified whenever we upload a new content. And then finally, don't forget to share this video to your friends so they can also learn. All right, thank you for your continuous support, and see you in the next class.